The title is Accelerating Quasi-Dynamic and Fully Dynamic Boundary Element Simulation by Hierarchical Matrices. So, yeah, this talk can be a seeker of Stephanie's talk. She beautifully introduced the recent updates of the basics and the recent updates of the hierarchical matrices. So I hope I can just avoid such complicated explanation of the H matrices. So I would like to acknowledge my colleagues. So for fully dynamic implementation, I have worked with Ryosuke Sato. He was my student now at University of Kyoto. And so Ozawa, he's now at Stanford. He was also my former student, and he worked on the quasi-dynamic implementations. So Tatsuya Hoshino and Akihiro Ida is a computer scientist and working for H matrices optimizations. All right. So needs for acceleration of computations. So recent inflation of model scales could be the reason for accelerating the computation. So Hyodo and Lee and Lu treated 3,000 elements and for the quasi-dynamic simulations. And for fully dynamic simulations, Ando and Kaneko treated 60,000 elements. So those are huge. So for the application purposes, we also need the more parameter studies in terms of friction for geometry or background sources. Of course, much more things have to be considered. But as you know, the bottlenecks of computational complexity in time and memory for dense matrices vector product is kind of huge. For quasi-dynamic simulations, the computational complexity can be n in the order of n squared. And for the fully dynamic cases, it can be order n squared times m. M is the number of time steps. Okay, so the outline of this talk would be more focusing on the theory and implementation of the hierarchical matrices, but I can avoid some basics. So I begin with the quasi-dynamic implementations. And as for the recent update, we implemented optimization for large-scale system with a new method called lattice H matrices. And then I talk about the fully dynamic extension by using the first domain partitioning method and the FDP-H matrices. So Stephanie mentioned a little bit about this method, so I would go into some more details about it. So before talking details, I want to mention our current achievement and the application so far kind of like this. For quasi-dynamic simulation, we could simulate AskX sequences on non-planar folds. For the fully dynamic cases, our current status is like 2D dynamic rupture simulations on non-planar folds without no penalization or polarization, I should say. And for 3D cases, our application so far is a wave propagation, not a rupture propagation. But this is implemented with the polarization, very efficient polarization. All right. So let's start the quasi-dynamic, quasi-dynamic case. But before that, I just want to mention that our formulation is purely based on the space and time representation boundary integral equations. We are not using Fourier domain or Laplace domain representations for our purposes. Yeah, good thing in the space and time domain is it's a good capability for the complex fault geometry like this. This is our previous modeling for 2016 Kaikoura earthquake. So many of branches and parallel and oblique faults exist there. But space and time domain boundary element method is capable of modeling this kind of complicated geometry. Okay, we can skip most of the thing here. And okay, I want to just quickly review how the order of complexity are evaluated. For the, if we consider the discretized form of a boundary integral equation, stress T at the element I time step n can be computed by the matrix vector product with the kernel here and strip history here for in terms of the space J and time M like this. So to do so, dynamic version boundary element method are originally needed to be the computation in the order of n square m like this. But for the static version of the boundary element, the summation is just run over the space J, like here. But the kernel here has n squared dependence here. So the complexity becomes n squared. So as Stephanie already explained, we have the method to reduce this large computational complexity. So our method for accelerating that kind of thing is H-matrices, of course. So for the quasi-dynamic case, we employed the lattice H-matrices accelerated by the Hakapuku library. And for the fully dynamic cases, these results are recently published. And for the fully dynamic case, we employ the two methods combined. One is a first domain partitioning method, and the other one is a combination of H-matrices. And the end, we have the new method called FDP-H-matrices, which were published last year. Okay, so the basics of the H-matrices can be skipped here, as Stephanie already explained. So the first attempt of introducing the H-matrices in our community was Otani et al. 2011. In her earthquake sequence simulation, she could beautifully beautifully shown the convergence of the numerical convergence of her simulation, and also the reduction in memory and computation time. So original boundary element method has an n square dependence, but H-matrices beautifully show the reduction like down to the order n log n like this. So we are motivated by her success. We further implemented the acceleration scheme called lattice H-matrices. please, for the detail, please refer. So there was recent publication just come out this month in GJR. Okay, what is a lattice H-matrices technique? So original H-matrices actually not compatible with the HPC environment. The reason is simple because the H-matrices has a very complicated internal structure in memory allocation. So this is one of the examples. The different colors show the allocation to the memory and CPUs and parallel computers. So different colors show the allocation to the different CPU memories. Because the H-matrix has such complicated structure, and this shows a counter dense matrices. This is a counter matrices, H-matrices. So those are very complicated. And in order to assure the load balance and kind of old-fashioned or the original H-matrices has to parallelize each processes. So complicated in a complicated way. As you increase the number of MP processes, the complication becomes worse. So lattice H matrices can solve this kind of complication. So by sacrificing compressibility or load balance to some extent, lattice H matrices configure the much simpler communication structure by separating the submatrices in this kind of square way, like this. So to do so, the original while the original H matrices has some complex communication has an order of n times NP. NP is a number of MP processes. The lattice H matrices reduce it to the order of just n. Yeah. So yeah. Okay. So the later part will be the kind of test of the efficiency enabled by the lattice H matrices. Okay, sorry. So this is just ads for our open source code for implemented lattice matrices. So although I opened the HBI open source code called HBI on the GitHub, so if you are interested, you can just download these softwares. All right, this is our scheme for cross-validation. So we use SEES project and SCEC benchmark test. And we just follow the basics of these benchmark tests. But okay, and this is an exemplified program we tested. In this test, we considered dipping fault like this, reverse fault like this, and rate and state friction assumed on the fault, and we compute the cycle of the fault strip on the fault. Okay, this okay, and then if we test the scalability of the scalability of this code, we can first observe the memory efficiency is following the n log n tendency like this. This is the original one, so you can see the reduction. And this is for the scaling for the computation time. And this also seems to follow the order n log n curve here. So we are satisfied in this result. Okay, this is a more important figure, important result for us. So this graph compare the parallel scaling, polarization scaling. So horizontal axis shows the number of MP processes, and then vertical axis shows the computation time. So blue curve here shows results from the normal H-matrices. Normal means without lattice H-matrices optimization. And orange curve here shows our result of lattice H-matrices. So as you can clearly see from here, normal H-matrices shows a saturation of the efficiency around the CPUs of the 100, like this. So normal H-matrices are not fitted to the large number of MP processes. And but for the lattice H-matrices, the curves are gentler. So for the smaller number of the MPIs, normal H-matrices are more efficient. But important thing here is lattice H-matrix doesn't show this kind of saturation. So if we use the very, very large number of MPI processes in the HPC environment, lattice H-matrix kind of optimization is necessary. Okay, this is a little bit more update about this kind of optimization. This is a optimization so-called contiguous memory access. As I said, because the original H-matrix has this kind of very complex structure, we can reorder and repack the memory assignment to the 1D array like this. To do so, we can optimize the OpenMP processes. This is cases without this kind of optimization, and this is with this optimization. You can see some tendency like this. So as you increase the number of cores or internal OpenMP parallelization, the efficiency can be worse as you increase the number of core threads. But by using this kind of optimization, the efficiency can be seen like this. Well, it's a little bit about the efficiency like this, but basically we can observe the kind of flat scaling like this, regardless the number of the core like this. So this kind of optimization is also used for the big scale computers. Well, this is kind of application of such a method in the actual fault models. So we have tested the scales of 200 elements, 1,000 elements, and 200,000 time steps for 200-meter resolution, and 150,000 years sequence of the earthquake along the median tectonic line located in southwest Japan. This was not so big, but the important thing is the computation can be finished around the time of 3 hours. So we can expect to extend this modeling size to the 1 million elements and 1 million time steps in this year. That work is still work in progress. All right, so the rest of time should be devoted to the explanation of the fully dynamic H-matrices implementation. So please refer these two papers for the technical and theoretical details. This paper is very complicated, but yeah, if you have any questions, please contact me or Daisuke Sato. All right, so the thing we have to tackle is that the original H matrix is only capable of considering the expansion in time. So that means the kernel matrices are referred as I and J. But in time, we have to deal with M here, which is in time. So what to do with time? That is our question. So by looking at the actual form of the space-time domain stress kernel, we can see that some systematic dependence on time and space like this. So main idea of first domain partitioning is that reducing the our computational complexity by separating the temporal term and space-time like this. So original kernels should have the dense matrix form like this. But if we can separate the X and T dependencies like in this way, the obtained final kernel can be explained by the product of the space-dependent vector and time-dependent vector like this. We utilize this kind of independence and approximation. So this illustrates how to separate the time and space terms. So as you know, the kernel or Green's function has a specific form depending on time and space. So we have the domain of wavefronts associated with P and S. And you also have some near field term in between P and S wave here. And also you finally have the static equilibrium domain like this, described by the static kernel like this. So as I described, these space and time dependence has their specific form for the different these three domains. So we have to separate the space and time. So how to do it? So for the wavefront domain like this, we need to approximate the kernel like for the some amplitude the term or describing the geometrical spreading, and normalized waveform term simply depending on time like this. But this decomposition needs approximation. For the near field term here, the kernel form, exact kernel form already has a separated form like this. So we don't need any approximation like this. And the domain of the static equilibrium, we already have the kernel only depending on space like this. Oh, this is just a quick note that due to the independence of time for the static equilibrium term, this method readily applicable for the earthquake cycle simulation, like a temporal truncation using the spectral VEM. But this is just a different thing. Okay, so all right. Once we could separate the kernel in terms of space and time in this form, our basic idea is applying the H matrices only on this special term obtained like this. And the temporal integration takes a different approach. So what happened for the integration over the time like this? But we don't worry much about it because the integration over time has at most order of 1, which is constant. This is the reason. So for domain of wavefront here, the range of time integration has a just a constant range like this from the onset of the from the arrival of the P-wave front, which is a kind of boxcar, a start initiation boxcar, and to the ends of the such boxcar function like this. Okay. Anyway, the range of time integration for the P-wave front or S-wave front just has a constant constant time length. And for the near field term or domain of inter-PS, we approximate the temporal integration by sparsely resampling the temporal points like this. This needs some approximation, but as you know, the near field term very quickly decays along the length. So this approximation doesn't have big rollback for the accuracy, numerical accuracy. And finally, this domain for the statistical equilibrium doesn't have integration over time, so that has no problem with it. Okay, so a bit more difficult part is how to conduct a matrix vector product in our FDP-H matrices. For the original H matrices, the matrix vector product is very simple because always the vector are referred from the same vector like this. Always mean the matrix vector needs to be conducted on the different levels of the submatrices, as Stephanie explained like this. But for any different submatrices like this one and this one, the same slip vector like this are referred. But for the dynamic case of the FDP-H matrices, the slip has a history in time. So we have to consider this, the thing that the submatrices have to refer the different part of the dense matrices be had like this, shifted by travel time like this. Okay. So for the larger submatrices, has to refer by referring travel time like this, but for smaller one, it can be so this kind of smaller or offset or travel time has to be considered. All right, this is too much technical details, so skip that. So we have tested the accuracy and efficiency by using the kinked fault, spontaneous kinked fault, spontaneous rupture on the kinked fault test program. So we just assume the linear simple weakening and initial crack and kick the spontaneous rupture. All right, and this is just to qualitatively compare that our progress of the slip rate. This is the time. This is the length along the fault. So it's very difficult to find the difference between them. Okay, and this is a more cross-looking of the dependence on the some efficiency controlling parameter. We basically confirmed the decrease confirm the convergence of the numerical result by decreasing the controlling parameter eta here like this. And we also found the huge reduction in the memory consumption and the computation time like this. So basically, these our method can attain the order n log n efficiency like this. All right.
Are you nearly complete? Because we want to leave time for discussion.
Sure. It's almost complete. Okay. All right. This is the current status, and we have implemented the method to the displacement wave programs. So 3D stress corner are work in progress, and the rupture simulation will be appearing later. All right. So this is just a conclusion. The H-matrices are found to be very useful way to accelerate the quasi-dynamic and the dynamics simulations. And yes, and for the details, please refer our available publication. Thanks for your attention.